The universe is 13.8 billion years old. That number is not disputed. The physics behind it has been tested across independent instruments, confirmed in cosmic microwave background data, and refined across decades of observation. NASA states the standard position without ambiguity. The early universe was extremely hot and dense, and what exactly triggered the initial rapid expansion remains unknown. But the math has a seam. Within the first 10 to the negative 43rd of a second, the equations of general relativity stop functioning. Not because of an error, because the theory was never built to describe matter at that density. The singularity at the origin is not a physical object. It is a signal that the language ran out, and the gap that signal marks is exactly where the first uncomfortable model enters. In certain formulations of quantum gravity, a black hole does not destroy matter. It filters it. The event horizon is a one-way surface. Nothing from inside escapes outward. From any external observer, the collapse looks terminal. But inside Einstein-Cartan gravity, the structure is different. Physicist Nikodem Popławski demonstrated that Fermion spin generates space-time torsion. At extreme densities, that torsion becomes repulsive, replacing the singularity not with emptiness but with a bounce. A new expanding region of space. What appears as gravitational collapse from the outside could, in this framework, register as a big bang from the inside. This is not metaphor. It is a line in the equations. The standard response is careful, unverifiable, because the event horizon seals the interior from any external observer. That is accurate, but it is a statement about observational limits, not a physical description of what happens to matter beyond that boundary. The singularity standard cosmology places at the same location is equally inaccessible and considerably less resolved. One black hole, one new region, but the structure compounds. In the 1980s, Coleman, Giddings, and Strominger worked on a related problem: baby universes. Not wormholes in the popular sense, but genuine contributions to the gravitational path integral, where space-time topology is not assumed to stay simply connected. The path integral sums over possible geometries. Some of those geometries branch. If branching topologies carry physical weight, then the Big Bang is no longer a singular event. It becomes a class of events, one of possibly many distributed across a structure that preceded it, generated it, and continues without it. The textbook still opens on page 1. But what holds the binding together may be considerably larger than the page count suggests. There is a question that standard cosmology answers by redefining the question itself, not what came before the Big Bang, but whether the word before applies at all. Two models press this from opposite directions. One says there was a before and it ran in reverse. The other says the concept quietly dissolves near the origin. The first model applies CPT symmetry, the combined transformation of charge, parity, and time direction, to the entire cosmos. In quantum field theory, CPT symmetry holds in every tested interaction. It is not a hypothesis. It is one of the deepest structural facts in known physics. Physicists Latham Boyle, Kieran Finn, and Neil Turok took it seriously at the largest possible scale. Their proposal, the universe after the Big Bang, is the CPT mirror image of a universe running from the same boundary in the opposite time direction. Not a different universe elsewhere. The same event, reflected across all three transformations at once. The model comes with observable consequences. Neutrinos must be Majorana particles. The lightest neutrino must be effectively massless. Primordial long-wavelength gravitational waves should be absent. A direct distinction from standard inflationary cosmology which generically produces them. The dark matter candidate requires a mass of approximately 480 million giga-electron volts for a stable right-handed neutrino. These are not decorative claims. They are predictions the model stakes its credibility on. The standard objection: no one can observe the anti-universe. The mirror half is causally sealed from ours. But the model does not request a telescope. It requests a neutrino detector and a gravitational wave observatory. The test lives in this half of the boundary. The second model moves in the opposite direction entirely. In 1983, James Hartle and Stephen Hawking published their wave function of the universe in Physical Review D. The proposal? Near the origin, time does not run back to a starting edge. It rounds off, the way a globe rounds off at the North Pole. There is no point further north. The question of what came before is not blocked. It becomes geometrically incoherent. The popular version of this stops at the relief, but the technical cost is rarely stated. To remove the temporal boundary, the model treats time near the origin as a spatial type coordinate. The problem does not disappear. It relocates from chronology into geometry. And what sits in its place is not an answer. It is a harder question. Why is this particular geometry the physical initial condition rather than simply a mathematically convenient one? Two models. One finds the mirror and measures it. The other dissolves the frame the mirror would hang on. The singularity is the most protected word in standard cosmology. Every popular account places it at the origin, the point where density was infinite, where time began, where physics stops. But infinite density is not a measured physical state. It is what an equation produces when the theory that generated it no longer applies. The singularity is not a discovery. It is the shape of a breakdown. Loop quantum cosmology replaces that breakdown with a boundary. In loop quantization, spacetime is not a smooth, continuous fabric divisible without limit. At the smallest scales, geometry becomes discrete, granular in a way that blocks the collapse to infinite density. The critical density in standard loop quantum cosmology models sits at approximately 0.41 of the Planck density. Not infinite, a specific threshold. When infalling matter reaches that value, the repulsive quantum geometry effect dominates. The collapse reverses. What classical general relativity records as a singularity, loop quantum cosmology resolves as a bounce. The objection from the standard side is technical but honest. We have no observational access to the Planck regime. That is accurate. But the counter is equally honest. The classical singularity also has no observational access, and it is routinely described in textbooks as if it were a physical event rather than a limit of applicability. The loop bounce does not add mythology. It replaces one unresolvable endpoint with a finite threshold that the equations can, at minimum, track. Before the bounce, there was contraction. How long that contraction lasted, what state it came from, whether its structure left any trace, those remain open, which is where the second model enters and raises the temperature considerably. Roger Penrose's conformal cyclic cosmology does not propose a bounce in the mechanical sense. It proposes a geometric continuity across what appears to be an absolute edge. As a universe expands toward its final cold, dilute, massless state, scale itself loses physical meaning. In conformal geometry, where only angles matter and scale does not, the remote future of one universe can be mathematically matched onto the hot, dense origin of the next. One aeon ends. Another begins at the same boundary with no gap between them. In 2010, Penrose and Vahe Gurzadyan reported concentric rings of anomalously low temperature variation in WMAP and boomerang microwave background data. They described them as potential signal from high-energy events in a prior aeon. The faint pressure of something that happened before our Big Bang, still visible in the oldest light we can detect. Their claimed significance reached 6 sigma. Within months, independent analyses by Moss, Scott, and Zeben demonstrated that rings with identical statistical profiles appear in standard simulated CMB maps, generated with no cyclic cosmology at all. The signal was not fabricated. The interpretation was contested. The anomaly did not survive as evidence, but the model did, because Penrose was not making a claim about one ring in one data set. He was asking whether the conformal structure of the cosmos allows for a seam, and whether that seam, if it exists, would leave a pressure mark in the oldest frequency we can read. The data did not confirm it. The question remains unresolved. The most persistent visual mistake in popular cosmology is the smallest one. The Big Bang is drawn as a point, a dot, something that fits inside an illustration. The explosion moves outward from a location, as if the universe detonated inside a larger, empty space. That image is wrong in the standard model and even more wrong in what comes next. The ekpyrotic scenario begins by removing the dot entirely. In 2001, physicists Paul Steinhardt, Neil Turok, Justin Khoury, and Bert Ovrutt published a model in which the hot Big Bang was not an explosion from a point. It was the result of a collision between two extended spatial membranes moving through a higher dimensional space. Brains. Our three-dimensional universe is one such surface. Another brain existed in parallel, separated by a distance measured in the extra dimension. That separation narrowed. The surfaces met. The kinetic energy of the collision converted into the hot, dense, rapidly expanding state that standard cosmology describes from its earliest accessible moment onward. The standard objection arrives immediately. We have no direct observation of extra dimensions. That is accurate. But the model is not invoking extra dimensions as decoration. It is using them to solve a specific problem. How to generate a hot, uniform Big Bang without requiring a singularity or an absolute temporal origin. The energy source is not a mystery drawn from nothing. It is the geometry of an impact. The model also challenges inflationary cosmology on its own ground. Standard inflation explains the uniformity of the early universe through a period of exponential expansion. The ekpyrotic scenario proposes an alternative, a slow contraction phase before the collision that smooths and flattens the universe without the inflationary mechanism. Two models, same observable consequences in some regimes, different physical histories entirely. The collision is local in the higher dimensional sense, but global across our brain. The Big Bang did not happen somewhere. It happened everywhere on the surface simultaneously, because the surface itself was the collision. That changes the architecture of the question. If our universe began as an impact rather than an ignition, then what filled the space between the brains before the contact? What governed the dynamics of that approach? And if the laws of physics inside a brain depend on the geometry of the compactified extra dimensions, on which configuration of fields and fluxes the space settled into, then the laws of our universe are not inevitable. They are one outcome among a very large number of possible outcomes. String theory compactification produces an enormous space of stable and semi-stable vacuum configurations. The number most commonly cited in technical literature runs to 10, raised to the power of 500. That figure is not offered as precision. It is an order of magnitude indicator of how densely packed the solution space is. Each configuration carries different values for particle masses, coupling constants, and the cosmological constant. Our particular set of physical laws is one address in that space. This does not explain why our address was selected. It does something harder to dismiss. It demonstrates that the selection exists. The fine-tuning of the cosmological constant, which sits at a value small enough for galaxies and chemistry to form, is not explained by the landscape, but the landscape at least provides a structure dense enough that such a value is not miraculous. It is statistically reachable, if there is a process that samples the space. Inflation was introduced to solve three problems. The universe is too flat. It is too uniform across regions that could never have been in causal contact. And it contains no magnetic monopoles, even though early universe physics predicts they should have formed in abundance. A brief period of exponential expansion in the earliest moments resolves all three, stretching initial irregularities smooth, pushing monopoles beyond observational reach, and synchronizing distant regions before they separated. The model worked. It fit the data. It became standard. What was not prominently advertised was the appendix. In a significant class of inflationary models, the field-driving expansion does not decay uniformly everywhere at once. Quantum fluctuations continuously push parts of the inflating region to higher field values, sustaining expansion locally even as other regions exit inflation and become hot, dense, expanding universes. The volume of inflating space grows faster than the volume that converts into thermal regions. The process does not end globally. New pocket universes form continuously, each one a local transition out of the inflationary background, each one from inside looking like its own Big Bang. Alan Guth, who first formalized inflation, described this consequence directly. The pocket universes produced in eternal inflation are not observable from within any single one of them. The boundaries recede faster than light can cross them. Our observable universe is one such pocket. The inflation surrounding it never stopped. This is the model that connects to the string landscape from Part 4. If the landscape provides 10 to the power of 500 possible vacuum configurations, and eternal inflation provides a mechanism that continuously nucleates new bubble universes, each bubble settling into a different vacuum as it forms, then the landscape is not an abstract space of mathematical solutions. It becomes a distribution of physical realities, each with its own particle masses, coupling strengths, and cosmological constant. The immediate objection from physics is not cosmological. It is statistical. If infinitely many pocket universes exist, and every event that has non-zero probability occurs infinitely many times across that ensemble, then the standard methods for calculating probabilities break down. Asking how likely our universe is becomes incoherent without a way to count, and no agreed measure exists. This is not a minor technical gap. It is a structural problem that Guth himself identifies as one of the most serious open questions the framework generates. The theory that explains our Big Bang as a local event also undermines the standard tools for judging whether any prediction from that theory is meaningful. The popular version of eternal inflation stops at the wonder, an endless sea of universes, each beginning with its own hot expansion, each running its own physical laws. That image is not wrong, but it omits what sits beneath it, a theory that began as a precision tool for explaining CMB uniformity and ended up generating a multiverse it cannot fully predict and a probability calculus it cannot fully repair. Our Big Bang was not the beginning of everything. In this structure, it was the moment one small region of an inflating background fell into a lower energy state and filled with heat. The background continued. Other regions fell elsewhere. The process has no known off switch and no known edge. Every model in this video assumed one thing without stating it. There is a stage. Space exists. Time runs along it. The Big Bang happened on that stage, whether it was a bounce, a collision, a bubble, or a mirror event. The final model removes the stage itself. The holographic principle did not originate in cosmology. It came from black hole thermodynamics. In the early 1990s, Gerard 't Hooft observed that the maximum information content of any physical region scales not with its volume, but with the area of its boundary, measured in Planck units, roughly 1 degree of freedom per Planck area. Jacob Bekenstein had already shown that black hole entropy follows the same rule. Stephen Hawking confirmed the radiation. The pattern was consistent across independent derivations. The interior is encoded on the surface. Volume may not be the fundamental layer. In 1997, Juan Maldacena demonstrated this concretely. A specific theory of quantum gravity in a 5-dimensional anti-de Sitter space is exactly equivalent to a quantum field theory with no gravity living on its 4-dimensional boundary. Not approximately equivalent. Exactly. Every gravitational event in the interior has a precise dual description in the lower dimensional boundary theory. Space-time in that class of models is not the foundation. It is the output. The standard objection is technical and legitimate. Our universe is not anti-de Sitter space. It has a positive cosmological constant, which places it in the de Sitter class. The Maldacena correspondence does not transfer directly. Holographic cosmology for our universe remains a research program, not a completed framework. But the objection describes a boundary condition, not a refutation. A team including Nia Yeshef-Shorty and Kostas Skenderis tested a class of holographic models against Planck satellite data in 2017. The models performed comparably to standard cosmology across a range of observational scales, particularly in the low multipole region of the CMB power spectrum, the large angle structure of the oldest light we observe. They did not outperform the standard model globally, but they were not eliminated by the data. A description of the early universe built from a three-dimensional quantum field theory with no space-time geometry, no inflaton field, and no classical expansion history remained consistent with observation within its tested range. That result did not make headlines proportional to its implications. If the early universe can be described, even partially, even approximately, by a theory that contains no space and no time in the conventional sense, then the question of what came before the Big Bang is not just unanswered. It may be asked in the wrong language entirely. Space and time might be the readable surface of something that does not itself have either. The Big Bang was not an event in space. It may have been the moment a quantum informational description transitioned into the geometric one we now inhabit and measure and call reality. The equations are still open, the seam is still there, and the oldest light in the sky is still carrying data we have not finished reading.